Hello and welcome to a video on complex zeros of a polynomial function. So the first thing we're going to look at here is the conjugate pairs theorem. And this is a pretty useful theorem because complex non-real numbers always come in pairs. So the theorem is just that if a plus bi is a zero, then so is a minus bi. That's it. All right, so this can be really helpful because that means you can never have one imaginary zero without having a partner or a conjugate pair that goes with it. So if we're looking at example 1, all that this is saying is information is given about a polynomial. Its coefficients are real numbers. Now, the coefficients are not the zeros. The coefficients are just the numbers before the variables, like 3x squared. The 3 is the coefficient. Okay. But even though the zeros are imaginary, the coefficients will still be real. And so we're just going to use the conjugate pair theorem to see what the pairs would be. So this negative I is like saying it's 0 minus I is a 0. And so therefore 0 plus I will be a 0. Or we can just say I. All right? Then we have 3 minus I is a 0, so it follows that 3 plus I will be a 0. That's all the conjugate pair theorem says. If negative 4 plus I is a 0, then so will negative 4 minus I be a 0. Notice that the conjugate pair theorem does not affect A. The real part stays exactly what it was. This is just a 3 for both, this is a negative 4 for both, and the 0 doesn't change either. All right? In this case, we have an odd, now this was an even one, so we pretty much are looking at 6 complex non-real zeros, which means this particular 6th degree function has no x-intercepts. Okay, this 5th degree function has it's going to have one x-intercept, but the other 4 will be conjugate pairs. So we're going to have the 0 minus I was given, so we know that 0 plus I, or just positive I, will be another one. And we have 3 plus I is given, so 3 minus I will be the other one. So we found the remaining 2. We were given 3, we found the remaining 2. All right, now how is this helpful? What we're going to see now is how we can use this to actually form the polynomial. So now that we know what the zeros are, even though they're non-real, we can still form a polynomial function, and the coefficients will still be real numbers. All right, so let's take a look. So if we have a 4th degree polynomial function whose coefficients are real and has the zeros negative 1, 2, and negative 2i, let's find the polynomial in both factored and polynomial form. So first of all, if the negative 2i is a 0, the other one would be positive 2i. Okay, so now we're looking at our 4 zeros. And so we can actually write our 4 factors now. So our function would be f of x equals x minus the first 0, which is negative 1. I should have said x minus negative 1. We'll change it to plus afterwards. Subtract the 2, so we have x minus 2. Subtract the negative 2i, so we have x minus negative 2i. And subtract the positive 2i, so we have x minus positive 2i. That's an I. All right, there's our polynomial function in factored form. A little bit of simplifying would be probably more likely to match an answer in the back of the book or on a multiple choice. So we have x plus 1, x minus 2, x plus 2i, and x minus 2i. We already know that when we multiply this conjugate, these conjugate binomials by each other, the i's will disappear. Let's go ahead and do that first because we want it in factored form, which is what we're looking at, and we want it in polynomial form, which means we just have to practice our multiplying and multiply all this out. So I'm going to multiply these two first and multiply these two first because I know that I'm going to get cancellations if I do that. All right, so with these two, I get x squared. The inners and the outers are plus 1x minus 2x, that's minus x. And then the last times the last is minus 2. Okay, when I multiply these two, I get first times first is x squared. The inners and the outers will cancel, and we get minus 4i squared, which is really plus 4. So to multiply this all out, I have to multiply this trinomial, x squared minus x minus 2, times this binomial, x squared plus 4. You can do that using a square. It's only 6 terms, so I'm just going to go ahead and push through it. I'm just going to distribute the all 3 terms over the x squared. So when I distribute the x squared plus 4. So when I distribute the x squared, I get x to the 4th plus 4x squared. When I distribute the negative x, I get minus x to the 3rd minus 4x. And when I distribute the negative 2, I get minus 2x squared minus 8. So now let's put this in descending order and combine what we can. And the only thing that I can see to combine is these here and here. So I have f of x equals the highest degree term, which is x to the 4th, minus x to the 3rd. There's only one of those. Plus 2x squared minus 4x minus 8. And that's a 4th degree polynomial. They have all real coefficients, right? There's no imaginary numbers in there. And this is the polynomial that has the 4 zeros that we had up there. All right. Now that's a 4th degree, and that was a fair amount of work. Now we're going to look at a 5th degree, which is going to be as long as it's going to get. We're not going to ever go 6th degree with these because it takes a long time. It's a lot of multiplication. Let's first look at our conjugate pairs. So we know 3 of the zeros are given, and we know if I is a 0, we know that negative I will be a 0. And we know if 1 minus I is a 0, that 1 plus I will also be a 0. So now we're looking at all 5 zeros, and we can write this pretty quickly in factored form. So f of x is equal to x. I'm going to have 5 of these basically. 1, 2, 3, 4, 5. And I just have to, each time I'm going to subtract the 0. So I have x minus negative 1. Oops. I have x minus I, x minus negative I, x minus 1 minus I, and then x minus 1 plus I. Okay? And just a little bit of simplification, and we'll have this in factored form. So f of x will be x plus 1 times x minus I times x plus I times x minus 1 plus I times x minus 1 minus I. Just getting rid of those inner parentheses there. Now I need to multiply all this out, and I'm going to multiply this pair because I know there'll be cancellations. And this, I know there'll be cancellations there too. So let's see what we have here. So we have x minus I times x plus I. Okay, and I got x squared plus 1 there. But this 3 by 3 is going to give me 9 pieces, so let's just lay it out with a little table. So we have x, we have minus 1 plus I, then we have x minus 1 minus I. And we just multiply all the pieces together. So we have x times x is x squared, x times negative 1, negative x, plus xi. And then the second row we have negative x, plus 1, minus I. And then the last row we have minus xi, plus I, and minus I squared. All right, now what can we reduce that to? Let's just write it right into here. All right, we've got the x squared term. There's only one of those right there. I'm just going to go by the diagonals, so there's x squared. We've got this diagonal, which is minus 2x, so minus 2x. We've got this diagonal, which the plus xi and minus xi cancel, but we still have the 1 there. But I'm going to join this one with this is also 1, so that's going to be a plus 2 at the end. Did I close my parenthesis? I didn't mean to do that. There we go. All right, and then I've got these 2 right here just cancel. So all I really got is the plus 1 here. I'll circle the ones that I really am left with here. I've got the plus 1 there and the plus 1 there. Minus negative, opposite of negative 1 is plus 1. So we got a plus 2. That's it. It's not that bad. It's still kind of long. We still have this 2 by 2 to multiply, and then we have to multiply that by these 3 terms. So let's go ahead and multiply the 2 by 2. I have first times first is x to the third. The inners are x squared. The outers are plus x, and the last times the last is plus 1. That is a 4 by 3. That's going to give me 12 terms when I multiply this out. So this, like I said, this is about as long as it gets. I'm going to make another table for these 12 terms. Okay, now I made the table 4 by 3, so I'm going to put the 4 terms along the side. X to the third, x squared, x and 1. I'm going to put the 3 terms on the top, so x squared, negative 2x, and 2. And then I'm just going to multiply them all out. So I have x to the third times x squared is x to the fifth. That's good because this is a fifth degree polynomial and I need one that's that high of a degree. I have x to the third times negative 2x. That's negative 2x to the fourth. And then 2x to the third. This is an x to the fourth here. And then this is a negative 2x to the third. And then this is a x squared times 2 is 2x squared. Then I have x times x squared is x to the third. Negative 2x squared when I get x times negative 2x. X times 2 is 2x. And then the 1. So just x squared, negative 2x, and 2. And again, we can look along these diagonals. We've got only one of those. So in my final answer, f of x equals x to the fifth. If I look along the diagonal with the fourths, I've got 2 things to combine there. That's minus x to the fourth. They combine to minus x to the fourth. And then the next diagonal, I've got all x to the third, so I can combine those. The 2's cancel, and I'm ending up with 1x to the third. Oops. And then as far as the seconds, x to the second, that's along this diagonal. So the 2's cancel, and I have 1x squared. This is third. And then the x's cancel. These x's here just cancel, and I just have a 2. There's polynomial form. And we can call this one here factored form. It's really, more than anything, it's just an exercise in how well you can multiply without losing a term, and knowing a little bit of basics to get there. Okay, I hope you found this video helpful.